Okay, now we're doing the last page, page 14. Number 9, consider the function e to the x over x. Does the graph of y equals f of x have any x or y intercepts? Okay, so let's do that first. How do we find x and y intercepts? We put 0 in for x, we put 0 in for y. So to find the y-intercept, we put in 0 in for x. Ooh, 1 over 0. That's infinity. Okay, no. Remember, vertical asymptote at x equals 0. Okay, so vertical asymptote at x equals 0. Good to know, good to know. Okay, now what about, that was y-intercept. What about x-intercept? X-intercept we set at y equals 0, and then we solve for x. Okay, so if we multiply both sides by x, we get 0 equals e to the x. Is e to the x ever 0? No. Okay, so no, there is no x-intercept either. Actually, there's a horizontal asymptote at y equals 0. Interesting. Okay. Does the graph of y equals f of x? Okay, we already finished that. B, discuss f of x as x approaches infinity or as x approaches negative infinity. Okay, if we put in infinity into this function, then basically we're going to get big number divided by big number. We don't really know what's going on. Okay, so if we put negative infinity, the top number, e to the negative infinity, is going to approach 0. The bottom is going to get huge. So it looks like when we go to the left, it's going to approach 0. Okay, when we approach the right, we don't really know what's going to happen. Okay, find and classify any stationary points. Okay, finally, we're going to take a derivative. So e to the x over x, we can use quotient rule or product rule. Remember that when we're finding stationary points and checking to see whether it's positive or negative to the right or left of the stationary points, if you have a choice to do quotient rule, go ahead and do quotient rule. So in quotient rule, the top is u, the bottom is v. U dash is equal to e to the x also. V dash is equal to 1. So let's fill in quotient rule, which looks like this. So v squared on the bottom is going to be x squared. And then e to the x on top. Okay, and then it says to find any classify any stationary points. Well, we know that there's going to be a vertical asymptote at x equals 0, right? And the top is going to be used to find the stationary points. So we just look at the numerator. And in order to solve this easily, I think it's better if we factor out the common factor. And then we get this. So e to the x, can that ever be 0? No. So we just ignore it. X minus 1, when is that 0? When x is equal to 1. So there is a stationary point at x equals 1. If we were going to draw a sign diagram for the first derivative, we would put that there is a asymptote at 0 and there is a stationary point at 1. And then we're going to check the 3 intervals here. If we put a big negative number into this here, we're going to get a positive or negative result. Well, a big negative number, remember this one's always positive, so we just ignore it. Big negative number into x minus 1 is going to give us big negative number. What about big positive number? Big positive number into x minus 1 is going to give us a big positive number. What about the number in between 0 and 1, which would be like 0.5? If we put 0.5 in there, it would give us a negative number. Okay, so here's our sign diagram for the first derivative. What kind of point is this stationary point? Well, it goes down and goes up again, so it is a local minimum. All right, find the intervals where f of x is concave up and concave down. Okay, in order to find concave up and concave down, we need to take the second derivative. So this is the first derivative. Let's take the second derivative of this function. Let's see, x e to the x minus e to the x. We could just I think it's easier actually if we take the derivative of this function, because then we're going to say, okay, u is equal to u to the x, v is equal to x minus 1, and we're just going to do product rule. Okay, so product rule, and we're going to multiply these across each other. So we'll get e to the x plus e to the x times x minus 1. That's our product rule result. So this is our second derivative, okay? And we want to know, let's see, I'm just going to simplify this. Is that right? I think so. So these two cancel each other out, so we just end up with x e to the x as our second derivative. And we want to know what the stationary points are, so we set it equal to 0. The only way this can be 0 is if x equals 0. So our stationary point for the second derivative is going to be 0 here, no asymptotes. If we put in a big positive number, this expression is going to be positive because e to the x is always positive. If we put in a big negative number, this expression is going to be negative. So this is our second derivative. It's not concave up or concave down all the time. It's concave down and then concave up here. Okay. Interesting. Okay. Combining these two is interesting, right? Because, like, look, to the left, I know it's going down and it's concave down. Between 0 and 1, it's going down, but it's concave up. So, oops. And then at 1, it flattens out, and then it's going to go up, and it's concave up. So it looks kind of like that, okay? All right, so we've done up to D. Sketch the graph showing, okay, we've kind of sketched the graph, but now we're going to sketch the graph on the on this graph paper. Oops. Okay, so at x equals 0, there is actually an asymptote. I'm going to draw it with the highlighter. And at 1, oops. At 1, something interesting happens, which is there is a local minimum. At 0.5, we know that it's going down. Okay, so do we have any other, x-intercepts and y-intercepts, we found out that it does not have x-intercepts or y-intercepts. So interesting. So if it's going down here, if it's going down here, it's never going to touch the x-axis, right? So at some point, it's just going to start going up, right? And it's going to be above the x-axis. For the left side, since it also, we know that there's no x-intercept, we know that we also know that the horizontal asymptote as it's going to the left is 0, so it has to be like that. Okay, and now we kind of know what happens when it goes to the right. We know it's going to just keep growing because we know that the first derivative is always going to be positive as we go to the right. So it has to be going up, and we also know it's concave up. So that's the shape. I guess the one thing you could do to perfect this graph is you could find out what is the value of the function at x equals 1. If we plugged in x equals 1, we get e to the 1 over 1, which would be 2.7. So it sounds like that this height is about 2.7, the value of e, right? Okay, and f, it says find the equation of the tangent to this function at the point where x equals -1. That is basically saying plug x equals -1 into the first derivative. So the first derivative was this, right? So if we put -1 in there, it would be -1 e to the -1 minus e to the -1. actually it'd be easier if we just did e to the -1 times -1 minus 1. So that would be -2 e to the -1, which is equal to -2 over e. Oh, it says equation of the tangent. The equation of the tangent. So this is just the m value, right? And then we need to find out the x1 and the y1. The x1 is -1. The y1 would be, if we put -1 into the function. So it would be this, -1 over e. Okay, and so if we want to figure out the tangent equation, it would be, write down point slope form, we put the m value here, we put the x value here, and we put the y value here. So it would be y plus 1 over e equals -2 over e x minus -1, which is x plus 1. Here is our tangent at x equals -1. It would probably look something like, you know, this is our tangent line, kind of like that, at x equals -1. All right. Last one. For the graphs of y equals f dash below, sketch a graph which could be y equals f of x. Show clearly the locations of any stationary points and points of inflection. Okay, this is like favorite test questions of the IB exam. So here they're giving us the derivative curve, and they want us to find the original curve. So remember, the derivative curves are showing slopes, okay, as heights. Okay, so the slopes of the f function are being shown as heights here. So if I look at the heights of the f dash functions, I see positive, I see 0, I see negative, I see 0, and I see negative. Do you see how I'm just looking at the heights relative to the x-axis? Okay, so if I was to draw a function which has this derivative curve, I would say, okay, this corresponds to a stationary point, so it would be flat. This corresponds to increasing. This corresponds to decreasing. This corresponds to flat again. And this corresponds to decreasing. So if I was to draw a smooth curve from this, I would draw kind of, you know, flat and down again, something like that. And then I could draw my y-axis. Now, do I know where the x-axis is? I don't. I could draw it anywhere, and I don't really know, all right? Because the f-dash graph only tells me if it goes up and down. It doesn't really say what the relative height of the whole thing is, okay? Let's do that again. So let's look at this f-dash graph, and we're just going to analyze the heights of the f-dash graph, and then we're going to conclude what would be the slopes on the f function. Remember, in the f-dash graph, the f slopes are drawn as heights. So let's analyze the heights here. We got negative height here, we got 0 height here, we got positive height here, we got 0 height here, we got negative height here. I'm just simplifying my curve into positive and negative and 0 values. So here is going to be a flat part of the function, right? Negative means it's going down to get to this flat part, and here positive means it's going to go up again, and then here it's going to be flat again, and then here it's going to be down again. So it's going to look something like this. You know, a good way to like make sure that you drew the correct function is if you just reverse it, right? We're more used to doing it the other way. We could say, okay, let's analyze when the function goes up and down. It goes up here. When it goes up, the derivative function should be positive. It should have positive heights, and that's really what happens, right? So if you are more comfortable going in one direction, check your work by going in the direction you're more comfortable with. That's it.